create 32 long startup names, and the end of the startup name might be a whole bunch of new lines, which indicates that like it's done. And that's fine. And so that's what we're going to be aiming for. We have a simple generator model here. Not trained, of course, just outlined. Doing a bunch of convolutional things to get you this, or convolving, I should say, on these sequences. We also have this encoder object, because initially what I want to do is train an autoencoder. So I make a model that's the encoder, then the generator, and then we'll be good to go. You train that, and then everything's all hunky-dory. Then you've got some basic generator to start with. I've got some web pages up. I'm like, oh, right, how do I build this GAN thing? Because what we want to do is have the generative adversarial network. So we're getting close to having this generative part ready to start. The adversarial part will be a relatively simple discriminator of true, false. So like, is this fake or not? And that part will get trained sometimes by your actual generator. It gets a C output from that. And sometimes with actual data. And so that's what the interesting bit is. And so you can like make a 50-50 chance of whether you train it with one or whether you train it with the other. Or you can just train it a bunch with this and then train it a bunch with the other. I'm sure there's a number of ways to do that. And we might have some cool way to do that. I don't know. We're not quite at that point yet. Right now, we want to be able to train this generator. So what I want to do is like read back in all my data. It's a new week, so of course I've forgotten everything that I've done. That's right, I had to make a special class. So let's actually auto indent, turn that off. TensorFlow taking a while to do the first import. Take your time, TensorFlow. No one's in a hurry here. There we go. I will run auto indent, of course, because I'm gonna run all this stuff. Bam! Cool. Then we're gonna read in our data. These are all different kinds of characters that are in our startup name set, of course, but we're only working with lowercase characters. Anything else gets thrown out. So you get Butch Baby something something CO, who knows. The Data Incubator. That's a cute name for a company. Fetch Coffee. You know, some of these. Trucknificent. These names are just so weird. Mufta.org. I'm sure it was dot. The Mitchell Group. Anyway. Every time I have to like look at that and just remind myself some of the silly things that are in there. We're going to place all the multiple spaces, which is a single space because I just don't need that much. I don't really care if there's multiple spaces. That to me is not particularly interesting. So we'll get rid of all. Same with multiple new lines. These are all the characters we actually have. A through Z, new line, and space. So there's 28, just to prove that. And they're in order this time. Unlike last time I had that problem. Alright, I don't really need this max unroll length business anymore. This is no longer an issue, because we're no longer doing that. Now what I need to do is convert this data into all of my 32 long startup names. That's what I'm going to have to do. That's right. Okay. And then we'll be able to build this model to do the stuff we want to do. Let us do that right here, in fact. So what I want to do is I want to see if I can do this with a sparse model. So rather than doing all the one-hot encoding, I want to put the actual integer of what the index is. So, I'll put a 0, a 1, a 2, a 3, so on and so forth. That'll save me a considerable amount of space. But I'm not 100% sure. It depends on the loss function that you get. So Keras, sparse categorical cross entropy. Sparse, there we go. Can I do this, but can I do this and have multiple, and do like the fully convolutional thing where I have multiple inputs, or outputs, I should say. You know what? I guess we're gonna find out. That's a very good point. So, can I do that for my input too? Because the encoder, well here, I said 32 by 28 because there's 20 things, but really it'd be 32 by 1 if I can get away with this. All right, let's see if I can get away with it. Let's make the data first, right? That's all my data. Sparse data, we're going to say data dot split. Split it out into new lines, right? And now, sparse data is all this stuff. Now it's sort of one per line, which is exactly what you want. But now what I want to say, I want this in a NumPy array first. I'm probably going to change this around. NumPy.zeros. And how many do I want? I believe what I want, what I really, really want, is I want this to be... I'm just going to like make this names or something. I want this to be length names long, comma, 32 is really what I want. And length equals 32. So I'll be generating names that are 32 long. And length. Whoa. Like that. There we go. With dtype equal numpy.uint8. I think that'll work. I'm going to find out. Okay. So now I have a bunch of... My data's not in there, so a bunch of zeros as yet. And I want to say for n in names. Okay, and I need to look this up. My char indices is what I'm going to do a whole bunch of lookups into. So I will say that sparse data of I. So I need the I here. There might be a more efficient way to do this, but this is probably going to be fine because there's not so many names. In fact, length of names, yeah, there's only 26,000. Length of set of names. How many of these are unique? That's actually good. A better metric. Length of set of names. Yeah, okay, so there's like 500-ish repeats. If you guys just had a startup name generator, you wouldn't have this problem. You wouldn't have repeat names. I bet most of those are the... counter? I bet most of those... hang on. I want to... are just like an empty string or a single space character or something now. Most common. Yeah, that's really cute there. I don't know why you don't... Can I just see like the top 10 or something? There we go. Test. HiveMind's innovative market solutions. Isn't there 6 times? Hive, Weave, Cloud, Lookup, Yellow, client of Roland and Associates. This is so weird. Let's transport. I guess that surprises me. This is not what I expected to see at all. Price Genie, Zosta. Why are these in there so many times? Quando. Okay. I stand corrected. Yeah, that's real weird. That is real weird. So what we're gonna do instead? Yeah, we'll make this the name length of set names, shall we? In fact, we're gonna make names a set. I don't want this nonsense. That's absolutely ridiculous. It's less data I have to deal with too. Okay. Sparse data of I is going to equal, we're going to take n, and for every letter in n, I want, I believe, char indices. Yes, that's what I want. I think this will be faster than looking it up every single time. Char indices of n, of nn, of c, the character, for the character in the name. I think this will work okay. Let's see. Can copy sequence with size 0 to access array with dimension 32. Oh, right. Right. So what we need to do here is temp is equal to this. And then we say temp plus yeah, 26. times 32 minus length of temp. So we fill up the rest with 26. That should be okay. Nope. Can I copy sequence size related to array with? Why would it have size 35? That is most strange. Temp. Length of temp. 35. How is it 35? Ugh. Okay. Alright, that was not what I wanted. So let's do this. N for N in this. No, I have no idea. I got an idea. We'll do this up to the maximum length. So we will cut your startup name short if it is too short. It is too long, rather. And that should guarantee that we all have a reasonable length. There we go. Sparse data. A whole bunch of things. A bunch of empty new lines. It's interesting. I should not be surprised at the first one. Like, you're not guaranteed in a particular order. Really? You just show me the whole thing? Okay, never mind. As I said, you're not guaranteed a particular order, so that just is what it is. Okay, so we have our, this is like our input data to our autoencoder. This is also kind of the output data. One thing I'm not sure about, is how this is going to play with this stuff. Sparse data.shape. Yeah, okay, let's try this. Get rid of that. And here, here we were generating 28 things. I feel like on the output side, you still won. Let me see. Sparse categorical cross entropy. Let's get that step. Keep the integers as targets. Blah, 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 blah. Oh, you still do the same kind of output, right? Character level, sequence to sequence prediction. Oh, okay. That's good. That's what I want. So you're doing, okay, this is exactly what we're doing. Sequence to sequence prediction. Essentially, make one sequence, spit out, ideally in this case, the same sequence. But you can imagine those sequences being different. This is some RNN LSTM business. And if I get this worked right, hey, you know, maybe maybe that would be what we wanted. Anyway, let's see. I think this might just work. Might just work. You're not putting in a sequence, though. What are you putting in here? 128 by 100. 128 by 100 by 256? What? Yes, the question is just what are you putting in that is the thing that we want? I'm sure if I just took the time to read this, but I can't like do that on stream. So I just have to try to figure it out live. As always. As always. I think if we just do this, but we say sparse categorical cross entropy, it will know, oh, I need to convert this, take this to the correct output. That's what this is telling me anyway. This. We're predicting 10 digits, but you're using activation softmax. So, I am looking forward to that. Okay, let us try this then. We made our data. That wasn't so bad. Gonna make this. Okay, that was all hunky-dory. Make our encoder. Whoa, something wasn't happy. What's the problem? Inconverted. Input 0 is incompatible. Oh, I see, I see. You really want there to be one channel on the input. I see. Can I just reshape it? No, we'll just do one channel instead. That's the problem. See? Yep. It really, really, really wants there to be a channel of some kind. So when we futz around with our data, we'll reorient it to do that. And of course, here they show you the compilation, and they one-dimensional like this. Interesting. One fixed model output shape. It still output 10 probability scores. Yes, that's as intended. Yes, okay, that makes sense. Now let's grab our model here. Sparse categorical cross entropy as before. Didn't like that. Okay, what's the problem? Oh, input layer is not 28, it's 1. Yeah. There, now the shapes all line up. Now we say model.summary. You've got your, the sequential 3 model, yeah, the generator, or the encoder, and then you got the generator, which outputs 32 by 28, so there's no getting around that. And then what we want is model.fit, and we always need to ask, how does this work exactly? X's, what is the input? The input is going to be sparse data.reshape, and I'm going to want however long it is by 32 by 1. And that should be fine. The target is going to be not reshaped. Right, I think that'll be fine. Not gonna worry about the batch size. Does it like pick some default batch size? Default does 32, that's fine. Epochs equals, just 1 for now, just to do something. I think that's a good place to start. Right, we're just saying eta delta for whatever reason. Let's see if this goes and see how long that takes. So it looks like it's going to end up taking maybe 30 seconds per epoch and has hot garbage accuracy. Absolute hot garbage. I think, however, it is doing what we expect. Keras sparse categorical cross entropy, multiple outputs. Only works on a single output. Okay, so someone posted an issue about this, so we might not be able to do this. Blah, blah, blah. Try updating Keras. Blah, blah, blah. This person... Output. Yeah, jeez, this model is... Whatever this person's doing is very goofy for me to see. I just cannot pierce through what they're saying. These two is fixed in this commit. Sparseness should replace the last name of output shapes with 1. Output shapes. This might be fixed. Not clear to me. Of course, someone still posted this problem. Keras module. It's a sparse version of Keras. Automatically for images to show this one. Doesn't seem to work as intended. I think it's just someone who needed to reshape but didn't. Oh, okay, now I got up to 40% accuracy. So I now believe that this is actually doing something. So in fact, if I make a word, if I make a name. Name is not a... Yeah, okay, good. If I make a name, that's whatever my WUCL wacky startup name is. I don't know. Foo Bar Labs. In fact, let me change this to Foo Bar Labs, where a hackerspace I used to be a member of. And then let me change that to the representation that Keras is going to expect. So name, numpy, whatever. Where it's going to be is char indices of n, no, for C, let's say. C in name. And then we'll also append plus equals, I guess, 26 times 32 minus length of name in and we'll say name np equals numpy.array of name np. Then what we can do is model.predict, and this is going to have to be a little goofy, right? Because we're going to get a bunch of probabilities out for each position, so we'll have to back convert all those, but we'll take care of that in a second. Name np dot reshape of, we're going to say 1 and however long it is, which is 32, but that's rather irrelevant. There's a name, just take a look at it here. That's right, this is the sort of format you're expecting. Foobar Labs, and then a whole bunch of 26. 26 is going to be an overly popular letter, particularly towards the end. So we'll see how this goes. This should do something. Error got it. Expect input 6 to have 3 dimensions, got array with, really? That's surprising. Do you have input shape? Input shape. None, comma 32. Oh, comma 1, of course. Of course. Comma 1. That's what I wanted. Dink. Now we got a bunch of probabilities. These don't look particularly exciting here at the end. It's like 26 is slightly higher than the others, and that's all it needs to do. If you scroll up towards the, you know what? I don't have to scroll like some sort of plebe. We just do plot dot imshow of preds. What is preds dot shape? Right. Okay. Plot dot imshow of preds 0. Bam. Okay. Yes, and you can see the 26 column here. As you advance down, becomes increasingly more likely. In fact, you want to show that here, color bar. I'll actually be curious. Yeah, this only goes up to rather low probability. But you can see some variability here and some variability at the end. I'm not sure what the deal with the variability at the end versus here is. That to me is a little odd. Most names, are like 12 characters or less, so it's not all super exciting. This is probably just the overall distribution of whatever these are. 3.6, 3.5, which is not all that different actually. So that's probably just random. But the model got up to 40% accuracy, which really surprises me. Anyway, let's convert that back. So what I need to do is take numpy.argmax of preds along axis and preds.shape. Let's take a look at this here. Equals 2. I believe this will give us what we want. And that tells you what is the most likely letter in every situation. I see what has happened now. We predict 26 everywhere, and 40% of the letters are 26. And that is why the model thinks it's doing so well, when in fact, it's doing terrible. Okay, so here's what I'd like to do. I would like to change the size of my data set from 32 long to 16 long. Yes, the names will be shorter, but we will have far fewer spaces. Okay, pal, what's your glitch here? I got too many of these. Too many 32s, and I should have end length. 32. That 32 is fine. Those are, no, this isn't fine. End length, there we go. Okay. End length, okay, that's good. End length. End length, okay. That should all be good now. Rebuild the model. Rebuild the data set. Better, stronger, faster. Faster, but actually slower. Yeah, okay. There's a few less. Can I do this on two-dimensional data? No, didn't think so. What if I reshape it? I'm just curious. what is the actual distribution? Actually, there's a better way to do this. Plot.hist, yeah, of sparse data bins equals 28. That's not what I wanted. I thought you were going to reshape that for me. I was wrong. There we go. So this is a distribution of characters. This is English. That's new lines, which is still a large number. That is wild. Like, would 12 be better? Now I'm questioning things. That's still so huge. That's wild. Like eight long names. Names are getting terribly short then. I might not be able to do this many max pools on the names. I'm doing 1, 2, 3, 4, 5. I don't want to be able to do 3. Rawr. This isn't that complicated. Show me the data. Okay, die. Yeah, okay, there it goes. Dead. Sometimes. Yeah, okay. If you go down to 8, that's a much more even distribution. Obviously, certain characters extremely unpopular. A, E, you know, your vowels very popular. Ooh, 8 though. That is rough. Those are short names. I think I do want to stick with 16 actually, and I'll accept this histogram as being what it is. What we need to do is remove one of these layers because we only have 16 things across now. Before we had 32, so we had sort of like 5 powers of 2. Now we only have 4 powers of 2. I think I want to get rid of this one. Over here. There we go. So we got to rebuild that model. That's fine. It's not a big deal. Not a big deal at all. We got our new sparse data, right? Shape. 16. Yep. Okay. Use a little less memory too. Always nice. So yes, there's other reasons other than memory to reduce your data like this. Okay. Make your new model, compile, fit. There we go. It'll train a whole lot faster too. So it's taking 15 seconds per training iteration. You'll see if this goes anywhere. Also, I might need to futz around with like learning rate and all this other nonsense. Things that you have to fix. Yeah, so this didn't go anywhere, right? We are ever so slightly above random, which is still hot garbage. But I guess that means we're not always predicting the same number. So that's a plus, right? Okay, got that. No, almost always 26. Not always, but almost always. That, and like spaces at the end? I guess spaces towards the end are sort of common. Alright, well that's a drag. But what I still want to do is fix this, and then for everything in here. Alright, hang on. This is the thing we're iterating through. I want to get back the characters for every single one. For name in this. Each one of these is a name. This is for I in. This is giving me an index, whatever the most common index is. And what we're going to do is indices to char of I. Right, I mean that's dumb. You could just use char list, right? Or chars, also fine. But this is gonna be good. Let's say out names. What's this? And then we'll .join. Right, so I'll just actually make this a list of strings. Oh, names. Oh, names. Yes, it's a whole bunch of new lines. Followed by use. Oh, I saw the 20s, and I thought that was a hex 20, hex 20, which is a space. But that's obviously not what it is. There's a regular N. That's cool. All right, I did not realize that. Okay, what I want to do then is let this train for like, I don't know. Well, I'll let it pretend to train for 100 epochs. It's not going to be allowed to train that long, but that's okay. While I think a little bit. So, this is an encoder decoder again. It's already thinking it's got the right answer. It doesn't though. We'll see if that goes anywhere. And there's no validation, of course. Yeah, that's extra fun. But we have a generator. We have an encoder. What we need now is a discriminator. And the discriminator will be trained on, it'll be given a real name, and sometimes it'll be given a name that's just created by the generator. If we give the generator, what are we feeding it here? 5 random numbers? 5 arbitrary numbers, maybe not random, is not the right word. Yeah, I'm going to futz around with this a little bit. Might be better things to do here. But it's climbing. The loss is improving, which is also good. Okay. So we need a discriminator model. And it is only 6, we got so much time. Time for discriminator. Which is our oracle who will tell us, is this true, is this false? It will give feedback to the generator. It says like, you fooled me, you didn't fool me. And that's how that's going to work. So what it receives is a name. A name in the same format that the encoder receives it. So, what I'm going to do is come over here, just so I can grab this stuff. We change encoder to discrim. Yeah, we'll just, for short. So it's going to be its own model. It's going to take in things of the same length. And it will just have to determine, is this real or not? We're going to have like an interface layer between the output of the generator and the input of the discriminator, because this generates probabilities, right? But we need to take like the argmax of those at every position. I assume there's a way to do this in Keras. I haven't, frankly, futzed around with this much. Reshape, dense, prod. Yeah, we'll have to sort that out. Like convert back. Or maybe you don't? I have to imagine you have to convert back to that. Oh, I guess if it's one hot encoded, then it doesn't matter. Oh, that's right. That's right. So this really will take a one hot encoded thing. Can I do this with sparse though? Oh, really? That would be convenient. I wouldn't need to save. Okay, let's see if we can do this. Sparse. Okay, sparse, Keras, GAN, input. No, discriminator. That's for generating. Yeah, I mean, because we're generating things in this particular way, it's a little bit goofy. Auxiliary classifier, GAN and Keras. Sparse gradients. Let's do sparse. Sparse activations, sparse gradients. These seem to be more about the gradients, which is unfortunate. Okay, but we're doing something a little funky, so. Like sequence discriminator GAN. Yeah, because they're not generating. That's annoying. Alright, well, that's fine. Then we will have non-sparse data as well. Let's make that. It's one hot data. One hot data set. We should be able to say there's like a Keras utils function to convert things to one hot encoding. Keras one hot encoding. There we go. Oh my gosh, this is. Yeah, there we go. Computes the one hot representation of an integer tensor. Not sure that's really what I want. This is like some indices, known classes. That might be what I want. Indices. I would have to double check. I think it's at utils. Let's go there and see what we got. Right, fine, we'll look at your silly web page, but like a lot of these machine learning mastery towards data, all this other stuff, it's not really what I want. Like I really just want the docs. Custom object scope. Categorical. Two categorical. That's what I was looking for. Converts a class vector integers to binary class vectors. Can be diverted from 0 to num classes. Two labels. Does it expect a 1D array? That's the real question. Let's stroll on down. It's going to be, not numpy. It's going to be tf.chars.utils. We can probably get away with that. Do I have tf? Yeah, okay, good. Two categorical. The thing is, am I able to just do this? Like, does that just work out of the box? Be amazing if it did. This accuracy is still, oh, it's probably overfitting, you know. I never actually put a train split on that. Validation split, right? Model.fit. Validation. There's like a split, isn't there? Yeah. Hang on. Is that how much my data is for validating? Should be used as validation. Yeah, okay. Validation split equals 0.1. Yeah. There we go. All right, let's see how it does on Foobar Labs now. You know, you got to train for a little bit longer. You're probably just as bad. Yeah, well, it got that those are not new lines, so I'm happy about that, frankly. Foo bar. I got this A right, okay. It got one letter correct. That is frankly progress. And you know what? Foobar Labs wasn't a name in the set, so I should not be surprised. Cool. We could let that train for a while longer. Actually, I went to recompile it. Yeah. Let that do its thing. Then we'll see how it really does in validation. It did not actually recompile, I don't think. Otherwise, the accuracy would not be this high. Interesting. Most interesting. Val accuracy, yeah, there's something. Yeah, okay, Val. I do not believe you. Oh, because all these underlying components still exist. That's what it is. So let's grab this. Let's grab all this. Rebuild that whole nonsense. Zoom. Oh, I wanted to run this though. Oh well, that was dumb. I am so suspicious of this. So suspicious. Like, that to me just does not make any sense. Really? I don't believe you. I do not believe you. I'm going to interrupt, because I need to understand this sparse data, how to use this. Sparse data. What happens if I do this? What does that look like? 1628. Did that just do the right thing? That'd be amazing. Oh my gosh, that's so convenient. That is incredible. That is like mind-blowing levels of incredible. Like, literally, I do not believe this. Almost. That it works on multidimensional. Life is so good. So good. No longer 1, but now 28. There we go. Cool. Right? One hot data dash shape. Groovy. So good. So good. All right. Now discriminator is going to do something similar to the encoder, frankly. It's going to be eerily similar. fact, let's do this. Except in the end, we need one number. Just one number. I don't want to do conv to the transpose. Thank you. Just one-dimensional convolutions is good. And I don't want this one here, I don't think. We want 1, and I want the activation to be... Gotta think about this. I need it to be between 0 and 1. I just have to double check. Is that just what sigmoid is? Where's the activations list here? Advanced activation layers. I want regular activation layers. Core layers, there we go. Advanced activation layers. The key value. Pre-value. ELU. Threshold. I'm sure it's a core layer. Activation. Applies a particular kind of activity. Activations. Here we go. Available activations. Exponential layers. Softmax. No, we don't want softmax. We want one output. Yes, no. SLU. Scaled exponential linear. Haven't seen that before. That makes sense. Although, okay. It's just like, this is going to affect your out. You just have to scale on the output side. Like it's the next weight. Not a big deal. Alright. Soft plus log 1, x plus 1. No, I don't think that's what I want. Soft sign, definitely not. Not really you. Dang it. Sigmoid. Sigmoid, right here. 1 over 1 plus x. I think this is what we want. Yeah, sigmoid. Let's go over here. Yes, 0 to 1. That is what you want. So that you can get bigger and bigger and bigger, and that just gets you closer and closer to 1. An S-shaped curve. Sigmoid. Okay. We were just saying yes, no, thumbs up, thumbs down. On is it true, is it false? And none of these will be called encoder. Encoder / discrim. Perfect. That is that model. Do I need to compile that separately? I don't think I do. Let's just make GAN equals sequential, I guess. Oh, I do. I am going to need, because sometimes we're going to read, it's going to get things directly, and sometimes it's going to get them from the previous model. That is right. Okay, so it doesn't need to be compiled on its own accord. Discrim. No, it's getting binary cross entropy. Optimizer, whatever, I don't really care. You can futz around with that kind of hyperparameter. I'm not particularly concerned by that. Yes, let us grab this stuff though. Change all this model nonsense to GAN nonsense. Okay. Input to the GAN, however, is not this. It's going to be whatever the output of the encoder is / whatever the input to the generator is. Generator.input shape. Input shape. It needs to look like, oh, come on. It has multiple inbound nodes with different input shapes. You're a liar. Two 256, apparently. How did I arrive at that? I don't even remember now. 1, 5. This is a mystery to me. Oh, it's a 5 long window. I see. Oh, because this keeps getting wider and wider and wider, but I keep making this smaller and smaller and smaller. Right. So I'm consistently at like 256, I think. Numbers. Which maybe I want fewer of those, but whatever. Actually, yes. I think that is true. Would like to do that instead. Yes, I got rid of the 128 there, so I should get rid of the 128 here. Yes. So I'll have to futz around with this a little bit, but that's okay. Is it still going to be 256? Let's find out. Coder.output shape. Yeah, it's still going to be 256. things that are of size 1, whatever. Who cares, right? But that's what the generator will take as input. So we'll randomly sample from that space of 256 floating point numbers. But that needs to be what it is. 256, comma 1, because whatever. That is what it is. We're not adding an encoder. We're adding a discriminator. Now, generator gets that. Then it goes into the discriminator, and you say yes, no. But I might need some interface layer, right? I need like this 2 categorical, or I need the opposite of that, right? I need to, no, hang on. No, this is fine. This is totally fine. It's fine, it's fine. Because this is exactly the output shape produced by the generator. Output shape. If you tell me multiple, you're so full of lies. You're full of hot garbage, you know? Hot garbage. Let's rebuild that, and then you tell me. Oh, put shape. Yeah, big surprise there. 64, 28, what? That's interesting. Okay, 64. That's... what? That's not right at all. There should be... yeah, there should be 16, right? You should generate 16 numbers, so that's definitely correct. This generator has gone wonky then. Gone very, very wonky. So what has happened here? Input shape 1024, 1. So this has gotten weird, right? Like, where did this 1024 come up? It's like, well, I can go back to the video last week and find out, when did I make this? Why did I do that? That's really what we kind of have to sort out here. And I must have decided, like, well, that's going to be my interior shape now. I think that's wrong. It's going to be 286 now. I'm just not sure how I came about that point. So I've got 16 here. Oh, and I'm doing 16 long, but I'm breaking it down every time. Hang on. Let's take a look at the encoder. Output shape. This output's 32 by 64, 64 by 32, 128 by 16, 256. Right, this is doubling its output here and shrinking its number of channels here. So you compute 64 things on 5x5 windows on all 16 shapes. Oh, they're making it bigger. So you're getting wider. Wider and wider and wider, but with fewer channels, okay? Okay, I can work with that. And these are all floats, of course. And I make it bigger 4 times. Ah, I see what happened. So, here's what the deal is. It used to be at 32. This is how many things I was doing. And I was doubling that 5 times. So 32 is 2 to the 5 times doubling 5 times, 1024. Now I only have 16. 16 is 2 to the 4, and I'm only doubling it 4 times, which is to say, times 2 to the 4. So my output size is going to be whatever my n length is, right? It's going to be my n length squared. Yes. Okay. That's good to know, because now, where did I have that 1024? Bam. Now we can fix this to be n length squared. And now we should just do the right thing. How did this work at all before? I have no idea. That's mysteries upon mysteries, my friend. Maybe I was using something else. I don't know. I do not know. Okay. Let's take this. come over here, get over here. Dot output shape. 16 long, 28. Now it works correctly. Bada bing, bada boom. Very nice. Okay, we got this encoder nonsense. Sure, whatever. Just to help. That's just to help like pre-train the generator a little bit. Give it somewhere decent to start with. You don't have to do that, strictly speaking. You could train your generator only on inputs from the GAN, but you know why kill ourselves here? In fact, let's rerun this on an empty model, like a model that we have not trained at all. At all. You should get hot garbage out here. That's amusing to me, that you get so much of the same thing based on the input. That tells me there's probably something wrong. So like somehow the structure of the model is collapsing in a weird way. That's very odd. Very, very odd. Not a fan. Like, are the predictions? Yeah, these should be all over the map, but they're not. Alright, well that's fine. Then you have your discriminator over here. Then you build your GAN from that. And this is not sparse categorical cross entropy. This is binary cross entropy. Right? Yep. Okay. And what you do is you make some fake data. And this is just data that's in the wacky space of the generator. Generator.input shape. Right? In this wacky space. And those are floats 32, right? Yeah. So they can be kind of like arbitrarily sized numbers in the like floating bit world. So what we're gonna do is like numpy dot float max or something. No. Floating point support. No. Like maximum. Let's say numpy random float 32. Let's see if that's a. Creating random samples unit distribution over yada yada yada. That's not really what we want. Instead, yeah, what is the largest? F info. There we go. That's probably what we want. Machine limits for floating point types. That's probably what we want. NumPy.f info. NumPy.float 32. There we go. It tells us what the biggest number is, the smallest number in all this other nonsense. So we'll do this. Dot random of size equals, I don't know, 1020. We should do just as much real data that we have. So let's see, sparse data dot shape. Yeah, just length sparse data. Sure. D-type equals numpy.float 32. You got that, but we're going to say fake data equals times equals, I should say. Excuse me. Let me get, what is a big number? And a big number is numpy.finfo of numpy.float 32 dot max. That's the biggest number there is in float 32 universe. Big data times equals big. Do this. D-type. I can't set a random. Crying out loud. I don't know why. You can't do that. That's one of the things that grind my gears. Just got to do this, do this, do this. Okay. I get a bunch of big honking numbers. Yes, most of them are in this range, obviously. You could have a smaller output range. You could just make a bunch of integers. Whatever. Who cares? Half of them you'll find are in this range. Half of them are in this range. You will not find any that are like, oh, +1. Extremely tiny chance that's going to happen, so don't even look for it. Okay, that's our fake data. Fake data.shape. That's not the right size, of course, because I need 16 of these. Hang on, hang on. Nope, not 16. I need n length squared. Yes, that is what I need. Exactly one argument. Well, sure it does, but I need this here. Okay. Do that. Fake data.shape. Now we're looking a little better. 256 random numbers for every single one of my inputs to generate some fake data, right? Got big, got this, got all this nonsense. Great. Now this should look the same. Great, it does. Cool. Now you should be able to say GAN.fit, and we'll say we'll train with fake data, right? That's like fake input. Yeah, okay. Yeah, so fake out. That is always going to be 0. These are all false. NumPy.zeros of simply like sparse data. Yeah, there we go. Should be good. So we're going to fit with the fake data. And fake out is the target. And epochs equals 1, just to see if this does something. Let me take a look again. That's summary. We're almost at time. That's okay. What do you know? Okay. So it needs to learn, you know, nothing is correct here, obviously. It doesn't really make sense. There's, yeah, it can just say, oh, always do no, and it will get to the right answer. But then you also need to train just the discriminator. And so you need to sort of do both these things all the time. And so you'll want discrim.fit, and you know it wants to get the real data. Discrim.summary, right? We have like 2 minutes here. It takes as input shape. Yeah. It takes as input the like one hot stuff. Right, that's why this is annoying. Oh, but I have one hot data. Okay, cool. So you put in, you know, one hot data. And the true out is, of course, by .ones of length to sparse data. Cool. And then you say true out. Oh, yeah, true out right here. And you say, you know, epochs equals 1, say, hypothetically speaking. Yes. And then I'm going to say, you know, for epoch in range, I don't know, 10. Just 10 times. And ideally, we want to mix it up and do a little bit of A, a little bit of B, a little bit of A, a little bit of B, whatever. Those kind of things. So you'll train the whole GAN, which will just train the generator as well as the discriminator, and then you train just the discriminator, so you have some true positives. And if we fix this up a little bit, we could train the, like, randomly pick what we're going to do each time, because otherwise it's just going to get real used to, yeah, being hot garbage. Yeah, it's like, yeah, it gets a little bit better, and then it's always right on these. And so you'll see the generator start to get better, you'll see the discriminator start to get better, back and forth, and back and forth, and back and forth. Yeah, actually, let me, validation split equals 0.1, just so it doesn't get to memorize all the data, because that's all it's doing here. Okay, let's come back out of there. Let's rerun all those models real quick, and then just set it going. Rebuild the generator. Yes, go here, do this. Oh, it's going to train. That's fine. It's not going to take too long. And I'm going to let this go all night. Not all night. I'm going to let it go for some reasonable amount of time. I think that's all we're going to have tonight, though. So we got a GAN implemented. We don't know how well it's working. There's a lot of improvements we need to make. But I'm actually super happy we got that sort of working. And it was relatively straightforward. It had a little bit of goofy bits here and there. Super nice with a Keras 2 categorical, doing exactly what I wanted in a multi-dimensional situation. Super good. I'm a fan. I feel like there's a good chance we're going to do this one more week. I don't know if I'll be available next week. I'm actually moving. So if my internet is working, it should be. We'll see. Yeah, now you can see the accuracy is not perfect. Oh, who knew? Who knew? That's cool. Yes, but that is all we got tonight. Thank you all very much for watching. I hope to see you again in the future. And don't forget, stay safe in the data mines.